Okay, so this is being recorded now. I can't tell, like, if any of you are live streaming this, I can't tell. So, hang in there, I guess. I won't know if you ask me questions. Do you guys have any questions before I get started? No?
Just here to, I guess,
soak it in. Okay. I'll try to make it work this time. Okay. I'll give them like one more minute. You said you know one person's coming for sure?
Yeah.
Okay. Well, I'm just gonna kind of coach you guys through. So like you guys are gonna do most of this stuff because I'm tired, a little sick. So you guys will be doing the problems and I'll coach you through how to do it, a few questions and all that. But before we do any of that, can you guys tell me what kinetics is? Like the whole chapter right now is on chemical kinetics. Like, what does that mean?
So it's basically the study of reaction rates in terms of chemistry.
Yeah, so for like someone who's not a chemistry major, what does that mean? Like what's a reaction rate?
It's the time it takes for a certain chemical bond to be broken. In
Yeah.
another form.
Yeah, so if we have like some generic reaction like A plus B goes to C plus D, right? Which one's the reactants, which one's the products?
Reactants on the left, products on the right.
Reactants, and these are the products. So basically our rate is telling us how quickly A and B are going to disappear and how quickly C and D are going to appear. So why is that important? Chemistry? Yep. Okay, cool. So like why are chemical kinetics important? I know we might not all be chemistry majors here, so if you're not a chemistry major, why do you need to know about chemical kinetics? Anything? Okay, do we have any bio majors here? Biomedical? Okay, well, metabolism, right? Your metabolism is just the sum of all the chemical reactions in your body that are using up nutrients and your muscles are moving and all that stuff. That's just rates, right? We're always talking about that. Or cellular biology, the rate at which materials come in, stuff flows out, ion transfer, materials being made, protein synthesis, all that stuff. And that's all just chemical reactions. So hi, come on in. It's a birthday boy. Happy birthday. So chemical kinetics is super important. And I don't know if we have any chemical engineers here, but I mean, your whole degree is basically how can we come up with chemical kinetics so that we don't blow a hole in a chemical reactor or make a nuclear meltdown. So this is super important, and it's definitely something that's going to stick with you. So I'll give you guys a choice. Do you want to do theory stuff and talk about more of that, or do you want to do problems?
Both.
Both? Which one do you want to do first? If you say problems first, then you guys have to come to them. Problems, okay. Yeah, it looks like it's you. Don't worry, I'll coach you through. And these aren't super tough problems anyway. Don't worry.
I want to teach me chemistry.
Okay.
Should I have my notes with me or anything?
No, I'll talk you through. These are just my notes because I took this class a long time ago. Okay. Okay, so you can erase that. And the
Erases.
oh, here.
I've never used it.
Oh, that's okay. So if you want to erase like a whole big thing, just draw a circle around it and then cut the middle. Or you can use like a regular eraser. So the first problem is that we're going to have a generic equation. So just can you write A plus B goes to C plus D? Good. And then can you add the subscripts like little a, little b, little c, little d?
Just under the same letter.
Do you remember how we did in class before, how we had like little a, big A, little b, big B?
As an exponent or as...
Coefficient.
Oh, okay.
Sorry. Did I say exponents? I meant coefficient. Okay. So this is basically a generic chemical reaction, right? We have some A, some B, some C, and some D, and then they all have some coefficient, whether it's 1, 2, 3, 4, 5. That's stoichiometry from first semester. So going off of this, can you write some of like the general rate equations? Do you remember what they would look like? There's going to be, just in the reaction side, there's going to be generic rate equations that tell us how A and B disappear. Do you remember what those look like? Okay, how about I'll give you a hint. Have you taken calc?
Yeah.
Okay, so we know that it's going to be like an infinitesimal change, right? It's going to be a derivative. So it's going to be d something over dt, right? Because you're going to be changing something with respect to time.
So it would be like dA over dt.
dA over dt, yeah.
B over dt.
Plus,
Plus.
well, hang on. So let's think about it in terms of math. You can do the dA over dt, but do you guys know if it's going to be plus, minus, or equals for the b section? No? Okay. So that is right. So it's going to be that. But since a is disappearing, is it going to be positive or negative? Negative, right? So it's going to be a negative. And then how does the coefficient affect it? Because you have a.
Is it the multiplier?
It's a multiplier, but are you multiplying it by a or by the inverse of a?
Well, you just,
Plus, you're multiplied by the inverse.
so it's
Yeah, so you have 1 over a. Oh, sorry. Okay. Yes. dA. And is it, so A is the name of like a chemical, right? So right now what that says is you have the change in A over the change in T, but is the chemical changing or is it the composition of the chemical changing? Does that make sense? Is it
composition.
Yeah, so it's going to be concentration, right? So it's the concentration of A. Do you know how to write concentration?
It's brackets.
Yeah, you just put brackets around it. It doesn't need to be super neat. So does that equation make sense to you guys? Why we do that? Yes, no? Head nods, shakes, anybody?
What's going on with that equation?
Okay, well basically, have you taken calculus?
I am not.
Okay, so what d something dt is telling us is that means this thing is changing with respect to time.
Right.
So what this equation is telling us is that the concentration of A, so like if A is like carbon, that means the concentration of carbon, so like your molarity of carbon is changing with respect to time. So as, like, let's say, like, as time is increasing, since there's a negative, that means the concentration is increasing. And the more of it you have, the slower it takes. That's why you multiply it by the inverse, right? Because if you have 2 moles, so let's say A equals 2, if you have 2 moles of carbon, then it's going to be disappearing at half the rate if you have 1 mole of carbon. That makes sense to everybody? That's why we have the inverse. So then we need to come up with the equation for B, C, and D, right? It's going to be a generic equation for every reaction the same way.
So you add the one with B.
Does the rate of decay or does the rate of disappearance of A affect the rate of disappearance of B?
I don't think so.
No, it doesn't. So it's just equal. Yeah.
But
Pretty much the same format.
Negative again because it's going away.
It's disappearing, yeah. We all on the same page? Yeah. Good, and then there's only one thing different with the products. Do you know what the difference is between the reactants and the products?
Positive because it's forming.
It's positive, but the rate is still going to be equal. It's still going to be equal to 1 over C. And so you guys can use this for most problems, right? As long as you understand like how stuff's appearing, how it's disappearing, what's going, what's coming. This is like half of most of the problems, just being able to figure this out. So this is, I mean, I know you're not in the class, but if this isn't in your notes, then you should definitely have this.
I believe he vaguely touched on some of this at the end of class, but we had a quiz, so
Yeah,
he
yeah.
was just kind of rushing through stuff.
Today I know he was talking a lot about like linearity and like the different orders and stuff like that. Yeah, so we'll be talking about some of that stuff too. Okay, thank you. And you can have a break now. Somebody else want to do a problem? Anybody? It's a lot more fun if you guys do it. So otherwise I just have to listen to myself talk.
Joseph is making me sure.
You guys are gonna hate me.
I promise you guys will get more out of this if I don't just stand up here and talk. Because you guys already have a lecture, you know, this doesn't need to be a lecture.
You're a good SI leader.
Thank you. Thank you very much. Okay, so the problem that we are going to do, okay, so you can erase all that. Okay, so we have another just generic reaction. It's going to be 2A plus B. And that's going to go to C plus 3D. Okay, and then they're telling us that the reactant A, it's being found to disappear at a rate of 6.2 times 10 to the negative fourth.
So,
6.2 times 10 to the negative fourth. And that, do you remember the unit?
this was
10 to the negative fourth. Do you remember what the unit is?
moles per second.
Yep. Good. And that's almost totally right, but you're missing one thing. So you're close. The negative's not there. Do you remember we were talking about, so dA dt is going to be, that's the rate that's disappearing. And so the negative is actually going to be here, and then there's one more thing that's with it. Do you remember there's the little a?
Oh, yes.
1 over little a? Yeah.
So it would be. So this would be half, right?
Mhm.
In this case, it would be 3.1.
Yeah.
No.
And then now you could, yeah, now you can say it's negative. I just wanted to make sure that you knew it was before. Okay, so now for everybody else, if that's the rate that A is disappearing, and if we said that all the rates are equal, then what's the total reaction rate? Like if that's how much A is disappearing, do you guys know what the reaction rate is? You don't have to do any math. It's just, you can look at that, and you only have to change one thing about that number, and you have the reaction rate.
The sign.
Sign. So what should the sign be?
Positive.
Positive. So the reaction, since we know that this is the rate that A is disappearing, and since we said the rate of this is equal to the rate of that is equal to the rate of that is equal to the rate of that, the sign changes. If this is the rate that A is disappearing, this is the rate of the reaction. Just, this is the negative, whereas the rate of the reaction is positive. Right?
So you don't have to add in the B because it's all the reactants gone.
Right,
It's just
because,
one.
yeah, so the reactants aren't necessarily dependent on each other, at least not for this problem. The reactants aren't going to be dependent on each other. And since we know that this is the rate of A disappearing, the rate of the other stuff forming is going to be at that rate.
But you don't have to double it because there's a second reactant.
No.
Is the rate of reactant always positive? The reaction.
Reaction is positive.
Yeah, I think the rate of the reaction is always positive, as long as you're forming products. Unless it's a, even if it's a reversible reaction, you're still forming something. So yeah, I think that's always positive. So then, like, if this is on a quiz and they're asking you what's the rate of the reaction, just remember to make sure it's positive, because you are getting something. And the negative is telling you you're losing something. Good to go? And there's a part B and a part C, actually.
All right.
But if I'm also if I'm going too fast, too slow, make sure you guys give me a nod, because I don't know where we're all at. Good? Okay, so part B is going to be, what's the rate of change for B?
It will be the same.
Yeah, it's the same, just because they're all going to be set equal to each other. Okay, one more. What's the rate of change for D?
It will be the same. But
Well, but D has a coefficient, remember?
so in this case, no idea.
Well, let's write out the generic formula. So you have 1 over little d. So what's that going to be?
Right. 1/3
So if we have products, is it plus or minus?
plus.
Plus, yeah, good. So we have 1/3 change in d, good, over dt. And that's going to be equal to the total reaction rate, which we know is
Positive.
positive that number, yeah. And then there's only one thing that you have to do to get the appearance of d. What do we do to get the appearance of D here?
Divide.
Divide by a third? Multiply by 3, right? Because we have this, it's 1/3 the rate of dp, and this is the reaction rate, so you multiply it by
Oh, you mean
3
you're
on each
solving
side.
for DT.
Yeah, you're solving for
Okay,
dt.
I thought you were just doing the same as you did first.
No, I'm sorry. You're solving for dt. So you multiply by 3, and can you guys see it in your head if you know what that is? 9.3, yeah, good. So pretty clear on how that one is? Yes, no, questions? You guys are really quiet.
It is also 8 o'clock.
It is also 8 o'clock at night, I know. Thank you for coming to this, because I know it's late. I was in my pajamas, and I had to change to come here.
9.3 is the concentration of D, or it's
Well, so dt is the change in time, right? So we know that this isn't going to be dt because it's molarity per second. I don't know what the actual name for the unit is. Molarity per second doesn't sound right, but
it's molarity or it's moles?
well, it's big M,
Oh,
so it's going to be molarity, right? Because if you have the concentration, so
concentration. Is
Yeah. let's do a mini Chem 1 review. So if N is moles, what's the formula for molarity?
N over
N
M
over,
times weight, or M times volume.
very close, because then, so if it's N times volume,
I said M,
M times volume, what's M?
molarity.
Molarity, oh, you're saying N equals molarity times volume? Yeah, that's right. So then what's the formula for?
moles over.
Yeah, N over V, right? So big M is going to be concentration, which is moles over V. It's going to be little m, that's mass. So that's in grams, right? And so this unit is big M over S. And so that's how we know we get concentration, because that's N over V over seconds, because time is going to be in seconds here. So as long as the concentration is changing. Good? You guys are not as excited about kinetics as you could be. It's almost done. So I know you guys are in Chem 125. I'm in Chem 343 right now. It's basically this class, but with calculus. So we're doing all this stuff now. This was like my homework last week, but with differential equations. So this is fun. I'll give you guys a break and I'll do one of the problems now, unless someone wants to do a problem. Oh, okay, fun stuff. This one has a table, so this one you're actually gonna have to write a lot.
You want to do it then?
Yeah, if you want, yeah, sure. You'll get way more out of it if you do it.
All right.
You'll have to write a lot. You can use whatever color. Okay. And do you know how to like move it up and down and extend the page, all this stuff? Yeah, you can move it here and then you extend the page. Okay. You know, you can look at my notes. Why don't you, can you write these 4 rates up there? Yeah. Just write that up there so that we can all get the data down.
Is that just those 4 lines?
Those 4 lines, R1, R2, R3, and R4. So we're going to give you guys a chemical reaction, and we're going to give you 4 different rates. This is an initial rate problem. You did one of these in class. So he's going to give you 4 different ones. What's K?
The constant that's dependent on the actual reaction.
Yeah, good. And it's probably hard to see, but the coefficient to that is a little m.
Oh,
It's a little baby m coefficient.
like up here.
Yeah, like monkey. Yeah. The next one's n like Nutella.
Wait, coefficient is an exponent?
Yeah. Exponent, I'm so sorry. So he's going to give you these 4 rate equations, and then we'll write the chemical reaction up there, and then we're going to be finding K coefficient, I think, for this problem. I don't actually remember which problem. Yeah, there's a lot of algebra in this section.
-4, yeah.
Yeah, -4 L over S. Next time I'll type these out. Sorry that you guys have to like sit here while we grade all these. So these are different rate equations.
Now I understand why Melissa used to take her time to write them everything.
Yeah, I should do that too.
Those markers are tricky.
Yeah, the smartboard's actually kind of tricky to use.
Smartboard's not very smart. Maybe I should stop talking. Play on my phone.
Okay, we're halfway there. Okay, while this is going on, true or false? You can look at an equation and tell the rate.
False.
False, yeah. So all rate stuff is either experimental or you have to do the math. Do you guys know what catalysts are? That's a side note, but you guys ever heard about?
Oh, they help speed up reactions.
Yeah, what's a catalyst? What does it do? I mean that, but it does other stuff too.
It lowers the potential energy.
Activation energy. Yeah, okay, so,
Biology.
yeah, you were like a bio major.
Oh, mechanical.
Okay.
She's just around a lot of biomedics.
Yeah, okay, I get that. So yeah, here's a little real life example of this stuff, catalysis. We're actually going to do a problem on catalysis. That's super important because a catalyst is not used up in the reaction, and it lowers,
And it doesn't change.
and it doesn't change.
Oh, it doesn't change. It uses itself again.
Yeah, it's not destroyed, right? It's not destroyed, and it lowers the activation energy, so stuff happens more easily. That like everything in your body is catalyzed. Like stuff in your stomach, if your stomach was just left to digest food and like break it down, it'd take a long time. It's a lot of catalysts in your stomach. That's what lactose intolerance is actually. The lactose enzyme breaks down and it stops working, so then the rate takes forever and the food doesn't get digested right.
Script.
0. Let me check.
But it's 2.
I think that's a 2.
Yeah.
I want to make sure you don't write down the wrong number. 0.266 to the n. And that equals 2.70 times 10 to the negative third m over s. Okay, and then it's going to be the generic equation, A plus D goes to C plus D. And then I promise you're done writing stuff.
So
A plus B goes to C plus D. Okay, so what they want us to do is they want us to figure out the order of this with respect to A and B. So we're going to be solving for what the values m and n are equal to. So right now we need to get m on its own. You guys have any idea how to do that, given these 4 equations?
Take 2.
Hmm?
Take 2.
No, that's right, keep going. Pick 2 equations and what do you do with them? Wait, which ones do I use? You could do R3 and R2. You could do R3 and R2, but the problem with those is that nothing's going to cancel out. So the terms on the top and the bottom aren't going to cancel out because the exponents won't cancel out, right? So then you'll have a lot more algebra to do. So what if you use R3 and R1? Yeah, what about R3 and R1? Because if you do R1 divided by R3,
The ends drop out.
the ends drop out. So why don't you do that?
You said ends or m's?
Um,
Solving for m.
yeah, right now we'll solve for M, like mattress. That's gonna be hard to do. So here, you can have the book and you can look at.
Okay.
It's problem 11, and that has the table on it. I know this is a frustrating problem, but I like this one because it actually has a lot of stuff in it. So bear with it.
So we're dividing, so it's 1 over 3.
R1 over R3, and then solve for M. just so I make sure everybody's following along, why are we doing this? What are we looking for?
M.
M. Yeah, we're looking for M because that's the order with respect to
Activation rate?
A. It's with respect to the letter A. And that's some compound. So right now we're going to find out what order it is with respect to the rate of A.
Why A?
Because the problem is asking us to find A and B because we can solve for the reactants. So we'll do A, which is M, and then we'll do B, which is N. So we'll do that stuff.
So I can just cross these out.
Mm-hmm. Mm-hmm. Okay, and just to speed up the algebra, because I know you guys can probably do the math, and I want you to talk about the concepts. That's gonna, yeah, the k's are gonna cancel out, and that's gonna come out to 1/2 equals 1/2 to the n. So 1/2 equals 1/2 to the n. To the m. So the letter 2, or sorry, the number 2 is the m. Actually, I guess it doesn't matter. Well, like 1/2 to the m, but I guess it doesn't matter. So just as long as there's a 1/. You don't have to erase it, just put 1/. Yeah. So what's m equal here? Like plug something in for it. What if it was 0? Yeah, so that wouldn't work. So what if it was 2? You'd have 1/2 equals 1/4, which is, so it's 1. So what's the reaction order with respect to A?
A number? 1?
Yeah, it's the number 1. So it's first order, right? First order. Okay. So now we're going to do N. So what equations are you going to pick? N like Nicholas.
The units.
I'm sorry?
The units for that.
There are no units, actually, because everything's going to cancel out, right? Can you use...
First order is just in respect to the time.
So if we're writing out like the rate equation, like dA dt, that'll be with respect to time. But so what we just solved for here, wait, can you keep it here? So K is just a constant, right? So K here and here is going to be the same. So that crosses out. And so these 4 numbers actually don't have units on them right now, right? Or they do, we didn't write them, but these all have the same 4 units. So algebraically, those are all going to cancel out. So we're just going to have 1/2 equals 1/2 to the m power. So we don't have any units, which is why we're just going to get a number. So the rate for this equation with respect to A is first order. Yes, no?
Yeah, got it.
Cool.
Thank you.
Cool. And so this one is going to work largely the same way. And so I'll just tell you that this comes out to 1/2 to the n. Is equal to 3.35 times 10 to the negative 4. Over 1.35 times 10 to the negative 3rd. And since the concepts are the important thing, I'll just tell you that here n is going to be equal to 2. So, if n equals 2, what's the order with respect to b? Second order, yeah. So we found out A is first order, B is second order. So what's the overall order here? Third order, right? Because we have a first order, we have a second order. M plus n is going to give us 3. And so now the last thing we want to do is solve for K. Right? Because K is a constant, it's going to be dependent on the equation. Do you know how to do that?
Sure.
That's okay. So I'll give you a hint. K is going to be equal to the initial rate, which they give us. That's a count. Or, oh, actually, we can use any of these. So it's going to give us the initial rate, and then that's going to be over something. That's the equation. K equals the initial rate over something. Tip of your tongue?
I
Yeah.
wrote it down.
K is equal to the initial rate over something times something. And we couldn't. Yeah, okay, so you're really close. It's first and second, so it's going to be concentration of A times concentration of B squared. Because A is the first order and B is second order. So it'll be the initial rate. Well, let's use, I use 1.35 times 10 to the negative third.
So it's 1 over that?
No, so it's the initial rate over, so no, you don't have to raise it. So it's going to be the initial rate, which we're using as 1.35 times 10 to the negative third.
And
Over the concentration of A. We'll use 0.185. Times concentration of B, and then to the what power? Because A is first order, so times B to the second, yeah, good, because B is second order. Good. So we'll use 0.266 squared.
so this goes times.
Yeah.
266,
Squared.
the whole thing.
No, just the concentration of B, right? Because, let me write the formula for you really quick. So we'll have K equals initial rate over concentration of A, concentration of B squared. And so since we have these rate equations, can you just scroll up for me really quick to the rate equations? Since we picked, well, I guess you guys didn't get to pick, I picked this one, 1.35 times 10 to the negative third. From this, we know the concentration of A is going to be this one, because it's the nth power, and concentration of B is going to be this one, because it's the nth power. So we can plug those guys in, scroll down, and that's going to give us this. And so the initial rate, what's the unit on rate?
To negative.
You're close. M to the negative means it's something over M, right? So it's going to be M times something to the negative, or M
times
over something.
S, right?
M times S, so close. Okay, so we have M times S, right? And it needs to be the same thing as M over S. So what do we have to do to S? Negative. Is everybody clear on that algebra? Raising something to the negative power is like dividing by that to the power. You all good on that? Cool.
So doesn't have to be to the negative or anything?
No, because yeah, if we have like negative 1 this, that'd be 1 over ms, which doesn't work out from the math, right? These guys are unitless, whatever, and then we have m over s. So then this is going to be equal to m over s. Okay, thank you. I know that was such a labor-intensive problem because we're writing it out, but I'm just going to run through it once really quick to make sure we're all totally clear. So we start off with these 4 rate equations, right? And then we have our problem, or we have our equation AB goes to C plus D. And so when we need to solve for m, we pick 2 of these equations so that we can get m by itself. So we're going to cancel out n. So they need to have the same term to the nth power. So the B reactant needs to have the same concentration in both arms. There we go. Initial concentration. So those guys cancel out, and then we can solve for m really easily, and we get what rate that is, or what order that is. Then we pick the other 2, and we solve for n. And then once we have those, we plug it into our K equation, and we get our constant. Good? No questions on that? Am I going too slow? Am I going too fast? Okay, I'm just going to keep going then. You guys want to do another problem that involves less writing, or do you want to do theory stuff and take a break and just talk? Your review session, so you guys tell me.
Maybe theory.
Theory? Okay. I have some true and false questions, actually, that we can do. In here somewhere. Okay, so we looked at a first order reaction. You guys looked at a bunch of different orders for things. And so, do you guys remember what the graph of a first order reaction is? Do you guys remember what you're actually graphing?
Is the concentration on the top? I mean,
Yeah, no, it is.
concentration on that one's
It is, but you do one thing to the concentration. Remember what that is? Because we want it to be a straight line. We do. You're very close. Not the inverse, it's the, that's the same thing as the inverse pretty much.
1 over.
That's the inverse. No, it's the natural log.
kind.
So we do this and we get a straight line for the graph of a first order reaction, right? So if we were just graphing the concentration versus the time, would it be a straight line? No, which is important because sometimes you might get a problem with like a graph on it. You need to know how to manipulate the data. So super important to remember the graph of a first order reaction, you have the natural log of A versus T. So if you guys remember like the Arrhenius equations for these, it's the natural log of A, which is something that's easy to mess up on a quiz. Let's see. Let me grab my book and I will quiz you guys on some equations and things. Do you guys have equation sheets? Do you guys do that? Do you guys make equation sheets? You guys should make equation sheets for these chapters because there's so many and all of them have so many, like you can use it for first order, you can use it for second order, you can use it for zero order, and there's so many different parameters. You guys should have equation sheets. That's super helpful for this chapter. Okay. Okay, so what is, okay. Can you guys think about what half-life is? Half-life is all chemical kinetics.
Yeah, you're talking about radiation.
It's the rate at which like a radioactive isotope starts to decay.
And when it reaches, it decays half of its mass or its concentration.
That's right. So that's like what carbon dating is, right? If you guys ever hear of radioactive carbon dating, basically they're looking at the half-life of carbon. You guys remember what, do you know which isotope it is? For carbon-14 dating? Okay, yeah, so they take carbon-14 and they know the half-life on that. So they can analyze the amount of carbon-14 in it. And they can say, okay, well, we know the rate that this is decaying and it's just dividing by half each time. So you guys are probably gonna have some half-life equations. So remember that it's the half of the amount that you have at that time. So let's say you have 2 grams at first, then it'll be a gram, then it'll be half a gram, then it'll be a quarter. And so everything's just going to keep dividing by 2, divided by 2, divided by 2 because it's decay. Good. Let's see. I'm trying to think like what the most important stuff that you guys should know for this chapter is. This is kind of a dense chapter. Okay. So we just talked about the graph of a first order reaction. What's the graph of a second order reaction look like? What are the axes for that? One of them's time, right? One of them's always going to be time if we're talking about rate, because it's going to be something over time in any class that you take. If you're talking about rate, there's always going to be time. And we know we have a concentration. So what do you do for the concentration for a first order reaction? Or sorry, second order reaction?
Would it be 2 times natural log of concentration?
Close. So what were you saying originally? What were you going to do to concentration of A? 1 over. Yeah, 1 over. So if we have a second order, that's going to be 1 over concentration of A versus T. I'm going to erase this. If we have first order, that's going to be natural log concentration of A versus T. How about zero order? What happens with zero order?
Just the concentration.
It's just constant, right? It's just K. Because for a zero order, it's just going to be the K constant. Yeah. Honestly, I think the rest of this chapter is just practice. So how about we do one more good practice problem? Let me see one that doesn't have a bunch of data that you guys have to write up for. That's terrible. Okay, let's talk about zero order reactions. Somebody want to do this one, or should I do this one?
Okay.
Me? Okay. So we're going to do zero order reactions. Okay. So to do this stuff, you have to have time and you have to have concentration, right? Those are the two most important things when you're talking about kinetics. Time and concentration, we'll call it S, because that's what they call it. So 0, 20, 40, 60, and 100. So concentration is 1, 90, 0.90, 0. 60, 0.50. So the importance of note those problems are giving us different times, and for each of those, they're going to give us a different thing. Do you guys know what the equation for K is for a zero order reaction? That's like the other critical piece of these problems. You have to know what the equation is. You guys know?
Just equivalent to the initial rate.
I think so, but they didn't give us that. That's wrong. We don't have the initial rate. We have to find the rate. And so for a zero order reaction, there's some constant that we look for, right? What's the constant we're solving for? Reaction coefficient kinetics. It's in the word kinetics, the letter K, right? K is our reaction coefficient for kinetics. So for the other problem, we've had the equations, the initial state over the concentration of A, concentration of B squared. For zero order reactions, it's going to be a little bit different. Anybody have an idea? It's okay if you don't know. Okay, so it's going to be 1 over T times the initial concentration of A minus the concentration at that time. Does that sound familiar?
Say it again.
Vaguely. So it's going to be the inverse of T, so 1 over time, which makes sense, right? Because for our rate, it's going to be over time. And this is going to be the initial concentration, A naught. So how many at? So this is going to be concentration when T equals 0. And then you have, whoa. Sorry, I got too excited. This is going to be the concentration when T equals like X, whatever time you're looking at. Make sense?
I remember he mentioned it in class. So
He didn't mention this one in class?
I don't remember.
Oh, I thought you
Looking
guys.
at my notes, I don't.
I thought you guys did a zero order, but if not, then okay, you guys are going to learn about catalysis and zero order problems today, because you'll probably have one on sapling at some point. So knowing that we have this, how would I solve for K when time equals 20? So 20 seconds. Time is in S, and this is it. So we have the equation. What am I going to plug in?
1 minus
1
20
times 100 minus, or 120, or minus 1.9.
What's it?
0.9.
0.9? Yeah. Okay, and I can tell you guys that that is going to equal to 5.0 times 10 to the negative third. Oh, sorry. Well, that's in minutes, actually, not seconds, but it's the same answer. Okay. So how about when time equals 60 seconds? What do we do?
I mean, it would be the same value for K, right?
Yeah, you should get the same answer, but let's do the math anyway, because I'm excited about this problem. And I want you guys to see how cool it is that it works out.
1 over 60 times 1 minus 0.7.
which gives us the exact same thing. It's going to give us the exact same answers, which we know because for a zero order reaction, K is constant throughout the whole time, right? So these should come out to the same answer, and they do, which is awesome. Right? I'm not going to move on to you guys. Tell me that it's awesome. I'm so excited. So that's that problem, and then I have one more crazy long one that we can do. Or if you guys want, we can use the last few minutes and you guys can just ask me questions about other stuff. That's going to give me trouble. Or we can, what do you guys want? Problem, questions, leave early. What are you looking for? Problem, okay. So this problem, some of it, there's no wrong answer if I give you a multiple choice question about what you want to do. You can do whatever you want. So this one, we're going to be using the Arrhenius equation, and we're going to solve for temperature effects. And I think we have just enough time to do this one. You guys want me to do this one, or somebody want to write? Okay, thank you. I'm going to use blue. Okay, so the Arrhenius equation for a first order reaction, I know you guys have it in your notes somewhere probably, but I'll write it for you. K2 over K1 equal to EA, what's EA? E sub A.
Activation energy.
Activation energy, yeah, good. Activation energy over R, what's R? R is always the same thing in chemistry. That's K.
0.082.
Yeah, but like what's that called? The something coefficient. Or it's the gas constant, sorry. It's the gas constant. R is always the gas constant. And then this is going to be 1 over T1 minus 1 over T2. And the subscripts are telling us that everything's going to correspond. So this is going to be the rate at temperature 2 and the rate at temperature 1. Make sense? And so they give us these things in a problem, and you have to solve for them, but like, do we all know how to convert between Celsius and Kelvin? Go from Celsius to Kelvin, you add 273.15 exactly, right? It's an exact number. So they give us K2 is going to be equal to 0.46. K1 is going to be 0.038. Temperature 1 is going to be 293.15. Temperature 2 is going to be 313.15. So, how do I solve for activation energy from this problem?
You divide by what's in burning and activation rate and multiply by R.
Yeah, good. So I'm not going to go through algebra because we can all do that. But then giving us that is going to give us activation energy. And so there's something special about activation energy, which is important that you guys should always know the units, because the unit will tell you how to solve the problem. So the activation energy is going to give you energy per like the amount of stuff you have. And how do we quantify stuff in chemistry? Moles, right? So that's going to give us an answer, EA, in kilojoules per mole, which will work out once you do all of that. And so once we do that, let me see what they're asking in actually the rest of the problem. Once we have that, we can solve for K. Okay. So we know that K is going to be temperature dependent, and we know that K is going to be dependent on everything else in this reactor. But if we know the activation energy, we know R, we know the temperature, we can solve for the new K, right? So if we want to do that, like you have a problem where they want you to solve for the Arrhenius K value, you're going to need natural log of K equals EA over R. But this will use a different equation. Oh, sorry, I'm messing this one up. So if you know everything else and you just want to solve for k, you can use an alternate form of the equation, which is negative EA over RT plus the rate of A. And so if you use this stuff, this is an alternate form. And so the math for this, do you guys know how natural log and E are related to each other? It's kind of like you have log and 10. Right, so if we have something, like we have a natural log of something, how do I get k on its own?
K equals E raised to everything on the other side.
Yeah, you raise everything to the power, e to the power of that, right? And that'll give you k to e to the power of that. You can solve, and that'll give you your new rate constant. And we will not have time to do the math on that, but I trust you guys to do algebra. If not, I'll help you with algebra. But yeah, in the last 5 minutes, questions, comments, concerns, any idea about what's coming up later in the class, stuff you want me to work on in the next session? What are you guys thinking? Good to go. Okay, well, if you guys don't have more questions, then we'll call it for the day. It's getting late. Good to go? Okay. The only thing before you guys go is I'm also going to write up an email. This is kind of a problem-based course. I know not everybody can come to the session, so I'm going to write my email up, and you guys can email me questions throughout the day, too. So if you guys want to send me screenshots of the problems or things like that, feel free to do that. Oh, before you leave, it's a good thing. Yeah, I need you guys to sign in. Also, I brought cake. If you guys want this birthday cake, because I know it's your birthday.
There's more cake.
Happy birthday. And yeah, can I have you sign in before you leave?
Because of the. Yeah.
It was my birthday yesterday.
No way. You know, 50 years ago today, they had the worst snowstorm in Chicago.
Really?
A great day for a snower.
So A number and name. And if you don't know your A number off the top of your head, that's okay. Just put your
Okay.
name.
So how old are you now? Wow.
Getting old, buddy. Have a good night. Yeah, I'll sign it for me.
Should I sign?
I mean, if you want. Even if you sign in, you say you went to a review session, if it comes up that you went to a review session, which helps. So, why not? No, I'm good, thank you. Okay, I don't know if anybody's live streaming this, but if you guys are, I'm done, so good night.